In the early days of aviation, aircraft structures were designed purely using static strength principles. The structure was sized to withstand maximum expected loads with an adequate margin of safety, assuming the material remained undamaged throughout its life. No consideration was given to fatigue, crack growth, or repeated loading. This approach worked for early, low-speed aircraft, but proved insufficient as aircraft became faster, heavier, and more complex. As engineers began to observe fatigue failures, constant amplitude fatigue design was introduced. In this approach, structures were tested and designed using repeated loads of fixed magnitude based on simple laboratory fatigue tests. While this was an important step forward, it did not accurately represent real aircraft operations, where loads vary significantly from flight to flight. As a result, fatigue life predictions were still limited in accuracy. To better represent real operational conditions, variable amplitude or spectrum loading was introduced. This philosophy recognizes that aircraft experience a wide range of loads during different phases of flight, such as taxi, takeoff, cruise, turbulence, and landing. These varying loads are converted into equivalent damage cycles using cumulative damage concepts. This approach significantly improved the realism and reliability of fatigue life predictions. In safe life design, the structure is designed to operate without developing cracks for a predetermined service life, after which it must be retired or replaced. No reliance is placed on inspections to maintain safety, as crack initiation is assumed to be unacceptable. While this philosophy offers high safety margins, it is conservative and often results in heavier structures and higher costs, making it unsuitable for large commercial aircraft structures. Fail-safe design introduced the idea that a structure should not fail catastrophically after the failure of a single structural element. Multiple load paths are provided so that if one component fails, the remaining structure can still carry the load safely until the damage is detected and repaired. Although this was a major safety improvement, fail-safe design does not quantify crack growth or define inspection intervals, limiting its effectiveness on its own. Damage-tolerant design assumes that cracks or damage already exist in the structure from manufacturing or service. The structure is designed to safely carry loads even with this damage, provided the damage is detected and repaired before it reaches a critical size. This philosophy combines crack growth analysis, residual strength assessment, and planned inspections, and it forms the basis of modern airworthiness regulations for transport aircraft. Durability-based design focuses on preventing fatigue damage from occurring during the early and economically important portion of an aircraft's service life. The goal is to minimize crack initiation for a specified number of years or flight cycles, thereby reducing maintenance burden and repair costs. This approach improves long-term reliability and ensures that aircraft remain economically viable while operating safely. This philosophy recognizes that structural safety depends not only on strength, but also on the ability to inspect and maintain the structure. Structural details are designed to allow access for visual and non-destructive inspections, with damage locations that are detectable and repairable. Designing for inspection ensures that damage tolerance assumptions can be effectively supported throughout the aircraft's service life. Design against widespread fatigue damage addresses the risk of multiple cracks developing independently at adjacent locations and eventually joining together. Such damage can reduce structural strength more rapidly than predicted by traditional damage tolerance analysis. This philosophy requires special evaluation methods, inspection start points, and mandatory modifications to ensure that widespread fatigue damage does not occur during the aircraft's approved service life. The limit of validity concept establishes a mandatory operational life limit for an aircraft, beyond which it cannot continue service unless additional justification is provided. This limit is based on fatigue testing, service experience, and structural evaluations related to widespread fatigue damage. The LOV ensures that aircraft are not operated into regions of high uncertainty in structural behavior, reinforcing safety through defined retirement or extension criteria. Design for durability focuses on ensuring that aircraft structures can withstand fatigue, corrosion, and environmental effects over long service periods with manageable maintenance requirements. This philosophy supports safe operation while controlling maintenance escalation as the aircraft ages. It integrates material selection, corrosion prevention, and service feedback to sustain both safety and economic efficiency. With the introduction of composite primary structures, damage tolerance philosophy was adapted to address composite-specific damage mechanisms. Unlike metals, composites do not show visible cracking in the same way, and damage such as barely visible impact damage must be assumed to exist. As a result, composite structures are designed to demonstrate no detrimental damage growth through extensive testing, making damage tolerance an inherent part of composite structural sizing.